Good morning and welcome once again to National Science Week here at the Queen Victoria Museum and Art Gallery in Launceston, Tasmania. I'm Martin George. This morning with me once again is Chris Auguste. Good morning, Chris.
Good morning, Martin.
Together we run the Launceston Planetarium here at QVMag, where we introduce loads and loads of people to the wonderful sights of the night sky. And I'm delighted to have with us as our guest this morning, Christelle Auguste. Good morning, Christelle.
Good morning.
Christelle is researching tidal energy at the Australian Maritime College here in Tasmania. So today we're going to be speaking about the fascinating subject of the tides. Tides on Earth, tides in other places in the universe, and also tidal energy when we come back to Christelle a bit later on. Do remember that you can ask your questions online. Toward the end of the session, we will be endeavouring to answer as many of your questions as possible. But first of all, let's take a look at a quick and really fun video of tides themselves. This particular video was made by the City of Launceston, and it shows the southern end of the Tamar estuary in the region where a bridge is being constructed. A time-lapse sequence showing the tides rising and falling. To me, it looks rather like a pulse of the Earth going up and down all the time. Of course, these images were taken only during daytime, so we're only seeing the daytime tides here and not what happens at night. But it gives you an idea of the rise and fall. Chris will shortly explain why this actually happens. And you can see here that sometimes the tides are a greater extreme than others. They expose more land sometimes, and sometimes they expose less of the land. So there we are. I'll stop that video there. And what I'd like to do now is to pass over to Chris, who's going to explain to us why the tides happen. Chris.
Good, thanks, Martin. So, why do we have tides? Now, many people know that the moon has something to do with it, but just what? Now, the short answer is gravity. Every bit of stuff in the universe has a gravity. The more stuff, the stronger the gravitational force. It has an infinite range, but its strength reduces with distance. So, if it's the gravity of the moon that's causing the tides, why are there two tides a day? While the moon only passes over once each day. So first, we probably need to define what a tide is. A tide is a distortion in the shape of one body influenced by the gravitational pull of other nearby objects. Tidal bulges are basically long period waves under which the Earth is rotating. These waves are not vast quantities of water moving around the Earth, they're just variations in water level. Think of a garden hose or a rope. You can flick a wave into it, which will run to the end. But the hose itself doesn't move very far at all. In fact, the end that you're holding is probably still in your hand. It's important to note that it is gravity that drives the tides. It's not gravity that leads to the local tidal phenomena, such as we saw in the video, with the water coming up and down so dramatically. Here in Launceston, we're at the head of an estuary, the so-called Tamar River. Here, the tidal range can reach about 4 metres. This is because of local conditions. For example, northwesterly winds can cause higher and later tides than those predicted based just on the astronomical conditions alone. So what's going on? As with any complex system, it's easier if we simplify things a bit. So if we imagine a perfectly spherical planet, and it's in a perfectly uniform gravitational field, so no other objects nearby. Well, either no other objects or all those objects are nicely evenly distributed, so the gravitational pulls are equal. And we'll also imagine it to be motionless. Now, if we put an ocean around that, oops, that's a bit, my circles aren't as good as they used to be when I was much younger. apart from my wobbly circle, the ocean would be a uniform depth across the entire planet. Now things start to get tricky, because if the planet were rotating on its axis, such as the Earth does, this would create a uniform equatorial bulge. Now that is not a tidal effect. Let's imagine now that our spherical planet has actually got a moon. So I wanted to do this without notes, but it's so complex that I would get myself out of order, so I'm having to change pages every now. The gravitational forces of the two bodies are distorting each other and their oceans. Well, in the case of our Earth and the Moon, of course, we're the only one with an ocean. The gravity is stronger on the near side. So we've got the Moon out here, the Earth down here. We'll call this the near side and this the far side. So the gravity on the near side of the Earth is stronger. The gravitational pull of the Moon is stronger. So the ocean is moved towards the Moon somewhat. Over on the far side, it is still attracted towards the Moon, but it's much weaker, so not as much attraction. And the Earth itself, being halfway between the two, is experiencing a pull somewhat less than that on the near side, but somewhat more than that on the far side. So it too is pulled over. Now, this isn't really quite what's going on. Both objects are pulling on each other, but we'll think for the moment just of the oceans. This is how we get two bulges, because the water has been raised up here. It gets thinner down there, and it's raised up somewhat over there, because the Earth has moved within the body of water. Now then, these tidal bulges shouldn't be thought of as being due to the lifting of the water. They're a result of the water moving around. Hang on, I was reading my notes. Is it a problem? They're the result of the water moving towards the regions of the tidal bulge. But this moving is not a convergence of giant ocean currents rushing into the bulge. It's just small movements, small displacements of huge amounts of water over a huge area. So each little bit moves a little bit. So on our hypothetical spherical ocean, with a spherical planet with a global ocean, these two tidal bulges would pretty much explain the situation. But the Earth is not a smooth sphere. It has geography, continents, island chains, and other land masses and weather. All of these affect the local tidal conditions. Tidal currents are caused by local topography. For example, here on the Tamar, we've got Whirlpool Reach, where the tidal flow can get quite brisk. I remember many years ago when I was simply messing about in boats a lot more than I do now. We were motoring against the tide under the Batman Bridge. It took us about 45 minutes to go from the pile at the southern end of the reach to a beam of Redwood Island at the northern end. Because we had nothing better to do, we just turned around and went back. It took us 5 minutes to cover the same distance. So you can see there that the flow was running at pretty much the hull speed of the boat. Anyway, back to our tidal story. We've got the Earth rotating. Oh, if we could go back to the... So the Earth is rotating once a day on its axis. And so that means that a point on the Earth is passing through the tidal bulge effectively, because the tidal bulge is still aligned with the moon. Now, because we've got continents and land masses, as the water is hitting as the tidal bulge is hitting shallower water and land masses, it interacts with them and creates the local conditions, much like any other wave does. So it rebounds off things and it gets funneled through. Now, it's getting even more complex because the moon is also orbiting around the Earth and dragging the tidal bulge with it. So by the time the Earth has done one complete rotation on its axis, the moon will have moved somewhat around the Earth. And so the Earth, therefore, has to move a bit more to catch up with the tidal bulge. I'm running out of time. This ends up meaning that the tides run about 50 minutes later from one day to the next. Now, the sun is also affecting this. It's much more massive than the moon, but it's also much further away. So the end result of that is that it exerts around about 1/3 of the gravitational or the tidal pull on the Earth as the moon does. So what that also does is when the moon and the sun are lined up with the Earth, with that wonderful Scrabble word synergy, we end up with the two tidal forces adding together, and we get spring tides, very high highs and very low lows. So that's at full moon and at new moon. At the quarters, we end up with them cancelling each other out, and so the range between high tide and low tide is significantly reduced. Now, there's one other little feature about this that I need to mention, and that is that the tidal bulge is actually preceding the moon as it orbits around the Earth. So meaning that high tide will occur before the moon has crossed the meridian, the local meridian. And now, Martin, you might like to actually talk a little bit more about that.
Just briefly, before we pass over to Christelle, what is happening here is that we have what is called tidal friction. And it basically means that there's a drag on the rotating Earth. And even though we actually think the days are getting shorter because of our busy lives, in fact, the days are getting longer, but not by much. Every century, the Earth's day gets longer by about 1.6 milliseconds. In other words, just over 1,000th of a second. We are, though, slowing down, and as that's happening, the moon is actually moving farther away from us. The laws of physics basically tell us that that will happen. It's moving farther away at a rate of about 3.7 meters every century. And we can measure this by using the laser reflectors left behind by the Apollo astronauts, so we can measure the distance to the moon very, very accurately. But before we pass on to Christelle, I'd just like to mention a few other places in the universe where we have some tides. And I have some pictures here now to show you of, first of all, this is Jupiter's moon Io, which is a very, very volcanic moon. And the internal heat to produce these is being caused by the fact that the moon is being squeezed, but because of the tidal effects of Jupiter and the other moons, the gravity is actually changing the shape and generating a lot of internal heat. And it looks a bit like a pizza, but no, it's actually a volcanic surface. And we also have tides in other moons as well. For example, we have Jupiter's moon Europa here, which is an icy moon, which we now know has an ocean underneath. So the internal heat source to keep that water liquid is generating that, is causing that water to remain liquid. And once again, we can say that these are tidal effects. We also have tides even in whole galaxies. Here we can see two galaxies that are interacting with each other, and the gravitational effects, the tides being such that the force on one side of a galaxy is greater than the other, is drawing out its stars into weird lines and loops. And here we have another pair of galaxies that's interacting. These are called the mice, and we can see what we call tidal tails that are produced by these unequal forces that are all related to the tides. We also know that binary stars that are in pairs that are orbiting around one another, can be distorted by the tidal effects. They can be drawn out into sort of elliptical or oval shapes. So there's lots of places where we have tides. But let's come back to Earth. And I'd like now to ask Christelle to talk about her wonderful research about tidal energy here on Earth.
Thanks, Martin. Hello, everyone. So we are going to talk about tidal energy, and let's begin the presentation. So I'm a PhD candidate at the Australian Maritime College, and my focus is on tidal energy and sediment transport processes near the turbine. So tidal energy is one of the most advanced marine renewable energy. The economic potential of tidal resources is reliable when compared to the other type of renewable energy like wind or solar, as the tide has the advantages to be highly predictable. So how it works? It's like an underwater windmills. First, the water moves in and out with the tides. Then the turbine turns the generator to produce electricity, and after it's going on shore with cable to the grid. So tidal energy can become a great contributor to the energy industry, and the global potential is worldwide. As you can see in this map, this is the tidal estimation generation. So the first country who has the biggest potential is Canada, then it's in UK, and after it's in Australia. There is different type of design. The most common is seabed mounted turbine, as you can see at the top. So it's 3 devices with different shape. And there is one in development. It's a floating turbine, as you can see at the bottom, created by Orbital. So now we are going to Europe, in Scotland, where CIMAC Atlantis installed 4 turbines of 18 meters at the bottom of the sea in Scotland. Each turbine is on a foundation with a weight of 200 tons and with six ballast blocks to provide horizontal stability. Last year, they produced 14 gigawatt, which is like the equivalent of the consumption of 4,000 households. And this year, they produced 28. So it's very, very nice and very promising. So tidal energy is very active in Europe, and it's coming to Australia. According to preliminary study, there is promising site in Australia where tidal farm is possible. It's in Western Australia with King Sound, where it's the highest tide. Then it's in Darwin, near the Clarence Strait. And after is in Tasmania, in Banks Strait. So my study focused on Banks Strait. This site has been also identified by the Austin project. It's a project funded by ARENA, which aims to map the tidal resources in Australia and check its economic feasibility. So people in tidal industry are interested in this site, and they need to better understand all the characteristics in this environment. And one parameter is sediment transport. So why sediment? So sediment can be moved by a wave or current, and very often by both. Sediments are responsible for the dynamics of sandbanks. Sediment influences morphodynamics, erosion and accretion, like, for example, the beaches. And sediment influences offshore and underwater structure. So tidal energy is a clean technology, but it still faces challenges. Which one? The first is the uncertainty of interaction of turbine with the environment. The second one is limited full-scale environmental survey, as it's still at early stage of development. And the last one is the difficulty to acquire data to calibrate and validate numerical model. And you can see why. It's pretty rough condition over there. So this picture was taken during our first trip in Bank Strait in March 2018. And we spent 17 days at sea, and it was 10 days like this, so pretty rough. So to address these challenges, I'm developing a numerical model to investigate hydrodynamics and sediment transport in this site. To validate numerical model, we need in situ data. So with the Austin project, 3 field trips have been conducted in March 2018 and 1 last year. And we use a large set of instruments. So the first one is an ADCP, Acoustic Doppler Current Profiler. It's an instrument who measures current speed. In the middle, with a rocket shape, is a penetrometer to measure the strength of the floor. Then sediment traps I've designed with the detection team of IMC to have information about the grain size distribution. At the bottom, it's an optical sensor with a laser to have information about the particle size distribution. In the middle, it's a sub-bottom profiler to characterize the seabed. And then it's a grab sampler to have information about the grain size. We also survey the area with a multi-beam. And if you can see at the top, if we can, there is an image of the multi-beam instead of our heads. If we can just move a little bit. Come back to the presentation. Yeah. So at the top corner, you can see it's the multi-beam sonar who can characterize the seabed and have precise bathymetry. This survey was able to characterize tidal sand dunes near Clark Island. On this map, you can also see the station of the ADCP, the instrument who measures velocity. So this instrument is measuring all the current velocity in the water column, looking up, and we are just one looking down to have insight about the velocity near the seabed. With the sediment data, we were able to characterize a little bit more the area of Bank Strait and to know how was the seabed. So it's more coarse sand, which is a rocky area in the middle of the channel. Then with the sub-bottom profiler, we were able to compare the sub-bottom profiler to the multi-beam. So we did the multi-beam in March and the sub-bottom in December, so 9 months apart. We saw that the dune were migrating. And in the south part of Clark Island, there is huge sand dunes of 10 meters. And now we are going to modelize and have a numerical model of this to understand the migration of the sand dunes. So my numerical model is this one. With this, I'm able to characterize the area and to know what is the current speed in this area, in this strait. So here is a map of the maximum current speed. And in the middle, it's reaching 2.4 meters per second. So after characterizing this area, I added turbines in the model. I tested 2 tidal forms, one of 100 turbine and one of 300 turbine. And I'm going to show you the result. So this is map of the change in the current speed between the state without turbine with the state with turbine. So I model in 2D and in 3D. So for the tidal form of 100 meters, the spatial extent of the change does not go beyond 5 kilometers. It's more around 2 kilometers. But for the 300 turbine, the spatial extent goes beyond 7 kilometers. So there is more significant changes. The difference between 2D and 3D are not significant for the depth average velocity in this case. But after we had more insight, and we focused on the 3D model, and we are looking in the water column to see where are the biggest change. And the biggest change are at the location of the rotor, as you can see in the little scheme with the turbine. This is the layer where the change is the most important. Lastly, I just extracted a profile near the sand dunes with the bed shear stress. So the bed shear stress is a principal parameter acting on sediment dynamics. So now I'm trying to reproduce the migration of the sandbanks in my model, and after add turbine to see how they can influence this migration. So this project will provide specific data for future tidal developer in this strait and for the community. And like this, maybe in the future, we can be part of the blue economy and may have a tidal farm in Bank Strait. This is our future. Thanks for your attention.
Well, thank you, Christelle. That's all very, very interesting. And there is certainly a future there, obviously, and you're doing some wonderful work. We're just getting the questions up on a separate device here. But first of all, while I'm doing that, I wonder if you could speak a bit more about how those turbines are anchored to the surface. What stops them moving away? Is it just pure weight or?
Yeah, so if we can go back to the presentation, I can show you with the device. So let's see. Oh, I want to show you. So each turbine are located on individual foundation. So the individual foundation is 200 tons. And at the bottom, there is 6 ballast blocks of 200 tons as well. So this is like the anchor, and this provides horizontal stability. And like this is not moving at all.
Okay, so there's that looks pretty secure, doesn't it?
Yeah.
Really, very secure indeed.
Yeah,
yes, yes,
indeed. So, yeah.
yes. Now, I think you mentioned a few things about the sediment, the movement of the sediment, and I know you've been doing some work on that. So what's the latest on that you're working on?
So I'm just like working on trying to reproduce the migration of sand dunes, which is very tricky because they imply a lot of parameters. So in the numerical model, it's like difficult to have all the parameters like in the real life. So I'm just like doing 2D models and 3D models to have the reproduction of the migration. And for now, there is still simulation running right now. So I'm hoping on Sunday to have some good results and continue further with adding a tidal farm on it and see the difference between the natural variability and the influence of tidal farm. So hopefully it would be not significant. Like this, it would be promising to have a tidal farm in Bank Strait. So we will see, but stay tuned.
And are there any similar projects going on in other parts of the world that you're connected with? So
in Australia, they're still just preliminary study, but in Europe, so I was talking about like the MEYGEN project. There is another one with Nova Innovation further north of UK, and there is one in France with the company Sabella in Brittany, where I'm come from.
Right.
And so they are grid connected. So basically, there is 3 projects in Europe grid connected, and there is a lot of trial and underway who's coming. I know like CIMEC Atlantis, the company responsible for the MEYGEN project, have installed some turbine in China. So it's developing all over the world. It's coming.
Fantastic. And you chose Bank Strait for your research, of course, because it's very close to us here.
Yeah.
But and I noticed on an earlier paper you wrote, you have the tidal energy, the tidal flow in Bank Strait at different points. It's been measured. What happens in places like, for example, the English Channel, or are there is it more common to have the motion of water faster in a narrower place,
Yeah,
or is
so
there no relation?
If the flow is constrained, so like in the English Channel or between in Bank Strait between Mulsoro Bay and Clark Island, the flow becomes stronger because of the constraint. So that's perfect place for tidal energy. So yeah, that's why. But in the British Channel, there is a site called Alderney Race, and there is a lot of study on it, and very promising projects are going on over there.
Right. Okay. Does it tie in any way with wind energy? Is there?
It would be perfect to have like a combination of tidal energy and wind energy, everything grid connected. Yeah, it would be like a blue economy. Would be good.
Right. Yes, I recall seeing quite a number of wind farms off the English coast, actually, in the water. You're from Brittany. I'm from Kent, actually, and I go back there often, and I notice the number of wind farms. But so they can be tied in together to fantastic.
Yeah, and it would be like the same for Bank Strait because there is a wind farm at Mulsoro Bay, so we can. Yeah, I think there is potential.
An advantage, of course, for the tidal energy is that it's much more predictable.
That's it. Yeah.
Yeah.
That's the most important.
Yes, indeed. We don't appear to have any questions coming up on my screen at the moment, but we have all sorts of questions at the planetarium about tides, not just tides on the Earth, or we get questions about tides on other planets and so on. And a little while ago, I was mentioning the business about the Earth slowing down. It's a very, very slight amount. But we often get people asking, well, how much is it going to slow down? And how long is this going to take? What's going to happen? Well, as we all know, when we look at the moon's rotation has slowed down quite a lot over a very long time, and it keeps the same face toward us. The Earth doesn't keep the same face toward the moon, though. But actually, in terms of the laws of physics, it will eventually happen. And astronomers and physicists have worked out that eventually our day will be between about 48 and 55 days long. So in other words, the Earth is eventually going to turn much more slowly, but that is not going to be for a very, very long time. And I'm afraid to say that before that happens, unfortunately, the sun will have enveloped the Earth, certainly Mercury and Venus and the Earth, almost certainly the Earth anyway, and we won't be able to live here anymore. So we will never really experience that kind of thing. But what it does mean, of course, is that the Earth is not as reliable a clock as people hundreds of years ago thought it was, because it's slowing down irregularly. We have to rely on other methods for very accurate time, like our atomic clocks, which are accurate to a second in billions of years or some figure like that. So yes, the tides are very strongly connected with that, with the length of the day and so on. And we also like to do a lot of research on how the Earth has slowed down over history. And one of the ways astronomers can do that is to study old records of solar eclipses. Because when the shadow of the moon falls on the Earth, the location on the Earth where the shadow falls is dependent on how far the Earth is rotated around at the time. So by looking at ancient records that, for example, say things like it went dark as we were eating in the middle of the day, even comments like that are a great clue to scientists as to by how much the Earth has been slowing down. So there's a lot of work that's done on that, and it's all tied in with the tides. The science all comes together beautifully. In fact, with astronomy, we encompass so many of the sciences, don't we, really, Chris? And
well, yes, it covers just about everything. Basically, all the other sciences occur on a planet, which all scientific work is being conducted on a planet orbiting around a star.
Yes, that's right.
So we've got a foot in all of them.
And we're the best example of a planet we can study, really. And it's like the work Christelle is doing with tides, and that can all help us to understand a bit more about other planets even, because published papers on what happens on the Earth can help us understand more about tides in moons of other planets, and it all ties in together. We have astrobiology, we have chemistry, we have physics, all sorts of things. So there's a lot that we can learn. So we have a couple of questions here now that I can see up on my screen. What are the environmental impacts of both tidal or tides and wind? What are the environmental impacts? Perhaps Christelle could talk a bit about that.
So I will speak just for tidal energy, because for wind, I'm not sure. It could be like the same because of the foundation for offshore wind. So for now, for tidal energy, there is no proof that it's going to harm like the fish or the whales or everything. A lot of studies have shown that, by example, for the whales, they are going to avoid the device. So the device is going to turn and produce some noise in the water. So the whales are, I think, intelligent enough just to go away. And some studies have shown that when the turbine is not moving, it can be like an artificial reef for some fish. So it's a good advantage. So for now, it's pretty safe, I think.
That does raise an interesting question, of course. We know that sea life loves artificial reefs. Stuff starts growing on our devices as soon as we put them in the water. How would we go about keeping these things clean? Like obviously a good crop of barnacles growing on the turbine is going to reduce its efficiency, I would imagine.
So if it's at the bottom of the device, if you remember the shape of the seabed mounted turbine, I think it's not harm. And for now, the turbines are going to be inside where the bathymetry doesn't exceed 40 meters or 50 meters. So it's still possible to go with some IV or some robot to go and clean and have like some maintenance over there. So for now, it's not going to deeper water. And like other type of technology are developing to be in a shallower water. So it would be like maybe 20 or 10 meters. So it would be like even easier to go and clean and just check if everything is going good.
Interesting stuff. We have another question here from the same person. How realistic was the tsunami water planet on the movie Interstellar? Now, I'm going to have to admit something very embarrassing. I haven't seen the movie, but maybe Chris or Christelle have seen this.
Yeah, the one, I can't remember which planet it was, one of the planets in close to the black hole, the water-covered planet. And from memory, they landed. It was nice and shallow. This does segue beautifully into a comment I was going to make from something you said earlier too. They're there and they could see what appeared to be mountains off in the distance. But then they realized that actually it wasn't mountains, it was a wave coming. And this was not a tsunami as such. This was actually a tidal wave, this tidal bulge, because as I remember the movie, it must have had, well, from the black hole itself, the planet, the ocean was being pulled towards the black hole in a much more extreme fashion than our Earth oceans are pulled towards the moon. And the planet was rotating underneath it. And so in that sense, it was quite accurate, although I think it might have been breaking towards the top from memory, which is probably not very accurate. But the other thing that comes from that is the fact that the previous mission, which they'd gone to investigate, which had been lost months earlier, the wreckage they found showed that it had happened only within the last hour or so, which brings us back to our nice, accurate atomic clocks, which run at different rates depending on the gravitational field that they're in and the speed that they're going at. So I think we could have another whole show on relativity at some stage. Great fun. Yes.
Yes, indeed. Yeah, so in fact, it probably was fairly realistic in terms of the physics behind it.
Well, that movie generally had Kip Thorne working on it.
Yes.
At some of the early, so there were scientific papers written on the production of the effects for that movie. A lot of quite good information.
And indeed, tides are actually a form of a wave, really, when you think about it in that way. And it does, of course, raise the question about water, liquid water on other planets. I think we spoke a bit about this a few days ago, and certainly we know that there is a lot of water out there in the solar system and also beyond on planets, and presumably their moons in orbit around other stars. We can work out the mass of a planet and its density, even if we haven't seen it. And by making a certain series of measurements, it's possible to deduce that there may be some water in that planet. We can also analyze what happens when a planet moves in front of its parent star as the star's light passes through the atmosphere of the planet. We can work out that there is water in the atmosphere or some other kind of substance in the atmosphere. So there's an amazing amount, really, that astronomers can do without actually seeing what they're measuring. They make these measurements of the amount of light coming from the star and so on. And it really is wonderful what we've been doing over the past 25 years in searching for other planets. But we're really mainly talking, of course, about tides here on the Earth and the wonderful research that's being done and how it all happens. We do have a couple more minutes for questions. We don't seem to have any other questions coming through at the moment. I love this subject, I really do. And I sometimes go down to the water's edge and just watch over a period of an hour or two as the water's coming up and going down again. As I drive home, I cross over one or more of the bridges in Launceston, and I watch each day. It's a bit different because, as I think you said, Chris, the high tides don't occur at the same time every day. They're occurring a bit later. So I might see a high tide as I go over one of the bridges here in Launceston, but a few days later, when I go home from work at the same time, it's actually a much lower level of water. So that's something that people can watch as well. And it's some science that everyone can do for free. You can go out and have a look at these tides, the rising and falling water. And I don't know whether you mentioned, Chris, I think you might have done, about where you have a beach which has a very gentle slope on it. It looks like the tides are actually much greater than they actually are.
Yeah, well, people often refer to the tide coming in and out, which is, of course, not really what's going on. It's rising and falling. But across a beach where there might be a long, gentle slope, the edge of the water is moving backwards and forwards. The same with the tidal flow in an estuary like the Tamar, where the water is actually physically moving up the river, because it's that, and that again, as I mentioned, was not because of gravity of the moon pulling the water up. It's because the tidal bulge is coming around, the water level out at sea is rising, and water likes to maintain a level, so it runs up the estuary. It gets funneled as it comes up, so it gets concentrated, and so the range increases as we head towards.
There are some great places in the world you can see this happen. I think you mentioned one in Tasmania earlier on. There's a place called the Bay of Fundy and the Seven Bore in the United Kingdom as well. It really can be quite dramatic. We are about to run out of time, but I actually have a question for Christelle. Christelle, I can't recall whether you mentioned this, but do you ever get to dive to go down and see this equipment?
No, I'm not diving, but some people are, like some other researchers are doing this, and especially for sediment transport, to have like samples of the seabed. We have like some people who are diving and taking some cores to have like the grain size distribution and the grain size, information about it.
Right.
So some people, but not me.
Maybe one day.
One day maybe, yeah.
And speaking of divers, we've already met our colleague David Maynard on a couple of occasions this week during National Science Week. He's a very keen diver and very keen on everything that's going on under the water. And as we run out of time today, I'd like to remind you that we still have 2 more live streams coming up this week. Tomorrow morning at 10 o'clock, we'll have David Maynard, our Senior Curator of Natural Sciences, back here, and he'll be speaking with Catherine Pugh all about the Tamar. It's actually an estuary. It is not a river. So many people call it the Tamar River, and that'll be very exciting. And then finally, on Friday morning, I'll be crossing live to Elise Allender researcher on the ExoMars 2022 mission, Europe's next Mars mission. She's doing a lot of work on the camera on board that mission, and I'm really looking forward to hearing what she has to say as well. Well, I think our time is up. Thank you very much for joining us. Thank you, Chris, and thank you so much, Christelle, for giving up your time to speak with us today. I'll say goodbye from me.
And goodbye from me.
Yeah, goodbye. Thanks.
Thanks, everyone. Bye for now. Thank you.